Hello, everybody. This is a problem solutions, problem 62, in the course of MATH2099 linear algebra at University of New South Wales. In this question, we have a vector and we have a plane given in the R3. We would like to find out a basis for the orthogonal complement. We would like to find out the projection of this vector on the orthogonal complement. And we want to find out the reflections of the vector on the plane W. Okay, if you have, in this question, we are going to solve these questions in the most effective way. And I will explain what I mean through the solution. So the normal of the plane W is given by these equations will be the vector constructed by just taking the coefficients of this equation. So the 1 minus 3 minus 1, as we know, gives you the normal vector. And since you're in the R3, three-dimensional space, and you have a plane equation, which have dimension 2, and the normal vector is the one-dimensional vector space, which gives you everything else except the plane in R3 is one-dimensional, because one-dimensional, every multiple spanning by the normal will give you the orthogonal complement of that plane. So that's by the definitions of the orthogonal complement. Okay, so you have, now we would like to find out the projection of the vector in the orthogonal complement of this plane, which is W perp. In the formula, we have to use orthonormal basis. But orthonormal basis for this vector space, since we have only one vector, will be just a unit vector corresponding to this normal. Only thing we need to do is just to calculate the unit vector of the normal vector, which will give us the normal to normal basis for the orthogonal complement of the vector space W. Okay, what is the length of this normal vector? Length of this vector is the square of 1 square plus 3 square plus 1 square, which is just root 11. So the n divided by the length of n will give us a vector which has only unit 1. If you multiply this with an inner product by itself, you will find 1. Okay, since we have only one vector, we need to calculate the projection of W perp, projection of W on W, projection of V on W perp will be inner product of the basis element with V and the linear combinations with respect to linear combinations of the vectors. And this was the general, yeah, okay, I would like to show you the general formula, So the general formula, you need to have an orthonormal basis, and for the projection formula, you will multiply the vector with each orthonormal basis element that will give you the coefficient of the linear combinations of this orthonormal basis vector. Then this vector that you're going to obtain will be the projection of the vector on the W. It doesn't matter which vector space that you're using here. I mean, this could be W perp or W, as long as you have an orthonormal basis of a vector space, could be W or W perp, this formula will work. So this is formulated in another versions of it, but the same logic will work for us for this question, for the questions in our hand. My computer needs to be awake. Okay. So this is coming from that formula. So this is the orthonormal basis element, dot product vector, and orthonormal basis linear combination of it. So that's that formula that I showed. Okay. This one was you have 1 over root 11 from this vector and 1 over root 11 from this vector. So when you multiply together, we will have 1 over 11. Then we have n dot product v, and this is the vector, this is a scalar, and that's the vector. So if you calculate this scalar product, this dot product with n dot product v, and 1 minus 1, 1, minus 1, and the v vector is given here 7 minus 8 minus 2 in the question. That's the vector 7 minus 8 minus 2. If you multiply dot products with these two, we have my 33. So we have 33 with this number 11, and the vector n. 33 divided by 11 is just 3, and n is the 1 minus 3 minus 1. If you multiply it by 3, it will be 3 minus 1 minus 3. So this is the vector, which is the projection of v on w perp. Done. Okay, now the last part of this question is what is the reflection of the vector v in the plane w? And there is a formula for the reflection, which is given in your lectures. That is R is the reflection transformation. This is a matrix form of the reflection transformation. Reflection is a transformation. And we know that Weber transformation can be written, can be expressed as a matrix. And this matrix R is the reflections of a V in the plane W. So then N here is the normal vector of the plane. This is what's all about. And the formula here is this one. This is a dot product here. This is D and matrix multiplication here. There's a matrix multiplication with this one. So if D is a unit vector, then this formula will be deducted to, this is an identity matrix minus D, and the matrix multiplication of D power. And we know that N over N bar is the we know that this is N over N bar. This one is the unit vector. This is what we found, right? This is the unit vector because we will normalize the normal vector. Okay, so and N dot N, we know that from the above section is 1. So here we have this vector and the transposition of this vector. And these are coming from, it's just a constant from the first one. So this is the constant from there are two vectors like that we have, they are multiplying. So this is a constant. If you think this constant as in the matrix form, so this is multiplied with each element here, and it's multiplied with each element here. So you have two of those, so it will be just a square of it. So this is why we don't have root 11, but we have 11 here. Root 11 is 1 from here, and root 11, 1 from here. Root 11 times root 11, it will be just an 11. This is why you have an 11 here. So this is D and D transpose, and this is an identity matrix. So identity matrix minus 2, 11, and multiplication of these two. So this is a very simple multiplication because this row with this column is just 1 minus 3 minus 1, exactly. So you multiply this row with minus 3 will give you the second row, and you will multiply this with minus 1 will give you the last row. And now then you need to calculate this matrix equation. If you multiply, and that is basically this minus this in every entry. 11 minus 2 is coming, So what I'm doing that I multiply 11 over 11 here because it will be just 1. So you have 11 minus 2. I can subtract it. 11 minus 2, and I take the 1 over 11 on the as a common factor. If you multiply 1 over 11 to 11 here. I think it is clear, but that's what I'm doing here. This is 11 over 11, and I am keeping 1 over 11 as a common factor. And then I have 11 minus 2 for this one, and so on. There is a 0 here, nothing will change. So you have minus 3 minus 2 is 6, that is this entry. And this is 0, so that is minus 2 minus 1 is just a plus 2, and so on. So when you looked at this entry, which will be 11 minus 18, it will affect only the diagonal entries in that form and nothing else. So when we calculate this number, the matrix form of this reflection is this. Now we would like to calculate what is the reflection of the vector v. So this is a transformation, so we need to apply this transformation to the vector. The vector given to us is 7 minus 8, 2. All we need to do is just multiply this matrix together with this vector. So this is a constant, we can leave it here. So this times this will give us 9 times 7 minus 6 times 8 minus 2 times 2, which is this entry. 6 times 7, 7 times minus 7 times minus 8 is 56, and minus 6 times minus 2 is plus 12. 2 times 7 is 14, minus 6 times minus 8 is 48. 9 times 2 is 18. So if we calculate these numbers, we have 1144 divided by 11, we have 110.4. So this is the reflected vector under this reflection of the vector v. That's all for this question, but one more thing that I want to say. And this is a very simple way to do it. This is the maximum, this is the best effective way to do it. You don't need to calculate W, for example, when you're calculating the, you don't need to calculate W bar from using the, the null spaces of the transpose. You don't need to use to do such things at all. You can directly say because otherwise, if you have some other vectors, some other things to do, then you need to do more calculation to it. Why it is easier for this question because you have a plane and the complement, orthogonal complement of the plane is the normal of it. If the equations, if the plane equation is given to you, then to decide the normal is just a very straightaway process. It's just the coefficients of this equation, plane equation, gives you the normal, which is the spanning set of the complement of the vectors of the vector space of the plane for you. So this is why it made it very easy to calculate for this question. As you realize, this is just really a few lines of calculation for this. Maybe little takes calculating the reflection. It might take a little bit of matrix calculations, but other than that, finding the projection, finding the spanning set is very straightforward for this question because you have a plane equation in R3. Just because we know some facts about the planes in R3. Okay, that's what I wanted to note it in the end. Okay, thank you very much for listening, and all the best to you all. Thank you.